Welcome again. We are going to solve one more application of pressure exerted on the surface of a sphere by the nearby charges or due to the interaction of charges. And here is the problem. Find the force of interaction between two electrically isolated hemispheres of radii capital R and a small r carrying charges capital Q and a small q respectively uniformly distributed over their surfaces. So the problem is clear. The centers and the maximum cross-sectional area of the spheres coincide. That means their centers coincides and this cross-sectional area and this cross-sectional area, they both coincide and nothing else. And now we are going to solve this problem. So we are going to imply first the Newton's third law of motion, and that says if this charge q applies a force on this charge small q, and if this force is equal to F, this small q will do the same but in opposite direction with the charge q. And symmetry and other things, we know that the forces will be acting perpendicular to the planes dividing them, and these two forces are going to same. And we are going to do one more thing. I'm going to place one more hemisphere where I'm going to add a hemisphere of radius capital R carrying charge capital Q again to this sphere so that it becomes full sphere. It was hemisphere earlier, like this and now it has become a full sphere. I'm going to complete the sphere, outer sphere. And we know that the force acting on the inner sphere will become zero. So that means in the previous case, this left hand sphere was exerting a force like this, then this right hand sphere is exerting a force F exactly of same magnitude and opposite direction. This sphere on this hemisphere on this hemisphere is going to exert the same force F, so that the force on this smaller sphere will become zero. And now I'm going to use this result into this case, and I'm going to complete the smaller sphere, and it was earlier like this, and it had a charge q, and I added another hemisphere of the same radius smaller and charge q, and this hemisphere is going to exert a force F on this larger hemisphere, and this will of course going to exert the same force F on the larger hemisphere. So the net force acting on this larger hemisphere in this case is 2F. And our job was to calculate F only, but I can connect things like this. I can play games like this. And now I'm going to remember one more thing, that I had a problem once when we have a surface charge density of a sphere as sigma, and the pressure at any point was I got it sigma square by 2 epsilon naught, and if I can break the result, this will be sigma multiplied by sigma by 2 epsilon naught. And if at this point I can consider a small patch of surface area ds. The rest of the sphere is going to exert a force on it, and the rest of the sphere produces an electric field at this place as sigma by 2 epsilon naught. I have discussed all these things in an earlier problem. So this pressure is sigma multiplied by external electric field produced at a point. So I'm going to find one more thing, that the pressure at any point of this larger hemisphere, in this case, pressure at any point of this larger hemisphere can be simply written as its surface charge density sigma of the larger as hemisphere multiplied by the electric field acting on it. And I know the electric field here is produced by this small hemisphere, and that value I can simply write this is k q by r square, and not kq by r square, but it will be rather written as k2q, because the smaller hemisphere has charge 2q divided by r square. This is the electric field here produced by, at this point, produced by, at any point of the sphere, produced by this small hemisphere. This is the electric field. And since pressure at any point can be written as charge density of the surface, that is sigma multiplied by electric field produced, I have already written it, so I'm not going to write it again. And sigma r is simply here in this case is q by 2 pi r square, because it's a hemisphere, so its surface area will be 2 pi r square. And now I'm going to get the result, that is force is equal to pressure multiplied by projected area on this hemisphere, and the projected area is nothing but P, the pressure I already calculated, multiplied by its projected area will be pi r square. Of course, the projected area of hemisphere will be pi r square. And now I'm ready to find out the resultant force, and this will be pi r square multiplied by pressure force, that is q by 2 pi r square pi r square multiplied by sigma multiplied by k 2q pi r square. And the result, oh sorry, I missed it. I think the result will be kqq upon 2r square. That will not be equal to 2f. I'm again doing a mistake. I got 2f equals kqq by r square. That means f will be equal to kqq by 2r square. These trains are driving me nuts, because I'm on a train duty. Thank you very much for watching.